Yes, Bismillah Rahman Rahim. And today we discuss the topic from the root locus technique chapter, and the name of that topic is defining the root locus. So in today's videos, in this topic we actually take an example of auto tracking camera, and that is such type of camera which track an object automatically. That's why that camera is known as auto tracking camera, and we build up a system for that camera through which it automatically track an object, track a moving part. For example, if a person move from east to west, so it automatically move according to that person. So for that camera, or generating a function for that camera, we needed 3 to 4 things. The first thing is the sensor, which sense that object and move according to that. And the figure which I already draw for that generating that system function is, so this is the sensor. It senses the object. This is the subject position, initial position. So that position we give to the sensor, and also give a feedback path from the output to this system, and that feedback path is negative. I already discussed about this negative sign in my previous video. So after accumulation of these two signals, we give the resultant signal to the K1, which is the amplifier, and that signal will give to a new function. So this is the function for motor and camera. Motor is, through this motor it rotate, and how it rotate, by taking different value of gain and different values of poles. So according to that gain and that pole, the camera move through this motor, and at the result we get SCS, which is the output, and the camera turn into this position. So if you accumulate this, so these two will be equal to, if we simplify this whole function, we get this function. How we get this function? We get this function like multiply these two, so we get, because these two are in series, and anything in control system, if that are in series, we multiply that too. So it will be equal to K1 K2 divided by S into S plus 10. So now this is nothing is present in this part, so we take that by 1, and here it is 1. So let's suppose if this is, as I already discussed in my previous video, I draw here again that if you have such type of function, this is CS, this is the input, and this is GS. This is E, this is RS. So in such type of fashion, if we we represent that by HS divided by 1 plus GS into HS. So here HS is this one, this is the HS. So this, putting that value here, and GS is 1 here. So putting that value here, so we get K1 K2 divided by S into S plus 10 divided by 1 plus 1 into K1 K2 divided by S into S plus 10. So simplify it, we get K1 K2 divided by S into S plus 10 plus K1 K2. Let's suppose K1 K2 is equal to K. So it's become equal to K by a square plus 10s plus k. So this is the final function which we get, and putting that function here, k by s square plus 10s plus k, and we get this here k by s square plus 10s plus k. So putting this function here, so we get a simplified function just taking an input put here. So from these two whole function we get a simple function, and this is the output CS. So now just giving value of pole and gain, so you get the output, and camera work on according to this output. Now let's suppose for this function this is the second order function, so we get two roots. If this is third order function, then we get three roots. Okay, so now the two functions are so this is the table for driving whole function. The first function, one is pole and the another is pole 1 and pole 2, and this is the k value. So for k is equal to 0, one pole is at -10 and the other pole is at origin 0. So if we plot it on graph, so we get such like picture. Here for k value is equal to 0, we get -10. Now if we increase the value of k further, so the k value is increased as we go down, so the pole value get increased and move toward the right, while the second pole value move toward the left. And when the k value reach 25, then the pole 1 value is -5 and the pole 2 value is -5. So these value become equal. Now if we further increase the value of k, so we get a complex equation of both poles. Another question come in your mind, that how I find these values and how I draw this table. So I tell you that taking the k value is equal to 0 and put that k value in this equation 0, so this will be 0, this will be 0, so the whole function will be 0. So the output will be -10, s is equal to -10 and s is equal to 0. So two output come. If putting the value of k is equal to 5 here and simplify that by quadratic formula, so you get two poles, and that pole's location is as I already calculated and right there in table. So if you plot these two whole value in graph, so you get k is -10, so this is -10. So the for k is equal to 5, we get -9.47, and for k is equal to 5, so this is the value will be 9.47, so it will be here. For k value is equal to 10, so we get -8.87, and here for k value is equal to 10, so 8.87 will be here. 8 minus 8 minus 9, so 8.87 value will come here. For k value 15, so minus 8.16, and that will be equal to here near to 8. So for other rule, the second rule is for k value is equal to 0, so the value will be equal to 0, so that will be here. For k value is equal to 5, so we get -0.53, and -0.53 will come here. So this root will move toward the left and the second root will move toward the right, and when the k value is equal to reach 25, then the first pole value is -5 and the second pole value is also equal to -5. So here if at -5 both poles have the same value, which is -5 at k is equal to k is equal to 25. So now if you increase the value of k, let's suppose 30, so we get the real part -5, and for second pole also -5, but the imaginary value changes. So the imaginary value changes, one value here and other value here. So similarly, if you increase the value of k, different type of the poles will move along the y-axis, but the real part will always be same, -5. So if we watch to here, we have just the real value, and here also for second pole we also have real value. So as we know that if we have real value and that's value for second order quadratic equation, if we get the roots and that is real but unequal, so the system will be overdamped. Now if we have value is real and equal, so the system will be critical damped. If the roots are complex, then we have underdamped system. And if the roots are purely imaginary, so the system will be undamped. The graph for this different type of system is for underdamped. If we plot the graph for overdamped, we have such type of slope for overdamped. So this will be the transient, and this section will be the transient section, and this section will be the steady state section. Now for critical damp, we have such type of system. The graph will be same as for our dam, but the slope of critical dam will be higher. That's why the critical dam is very best. So this is the transient section and this is the steady state system. For underdam, we have such type of graph. At the start we get some oscillation, and after that oscillation we get a purely steady state response. For undam we have such type of response, always oscillating. So this is the graph. Now how we show this type of response, this type of roots in here? As you see here, if here we get at k is equal to 10, we have one root minus 8.87 and the other root is minus 1.13. So these two values are real but unequal, so the system at this value will be overdamped. Now if you take the gain equal to 25, so we get this minus 5 of one root and the minus 5 other root, so these two roots are equal. So at this point here, the system will act as a critical damp. Now for values more than the 25, so we get a complex value, and at that point the system will act as a underdamp. So if you plot such type of graph and you get this value here like this, so here the value will be, the real part is equal to 0 but the imaginary part is purely imaginary, so that's why at this point the system will act as a undamped, and the graph for the undamped is here. I already graph. So you plot such type of root locus. This is the root locus. and this is the straight line. So at this here the real, if you see to the real part, the real part is same, which is -5. So the real part is same, and we know that the settling time in time is the function of just the real part, and that is the inverse proportion of real part. So the settling time at this line will be same because the real part is same, so that's why the settling time will be same. Now if you see to the gain of this function, if you increase the value of gain, here the value of gain is increasing, so that's why the damping ratio diminish and the percentage overshoot increase. Damping ratio is the gain, and damping ratio is actually the inverse proportion, and if we plot that, and damping ratio is represented by zeta, and we know that the percentage overshoot is equal to e की power minus zeta x divided by 1 minus zeta square multiplied by 100. So this is the minus sign, so it means that if you increase the zeta, the percentage overshoot will decrease. So as I increasing the value of gain, the damping ratio get decrease, and that's why the percentage overshoot will increase. And we also know that the damping frequency is a function of imaginary part. So if you see here to graph, the graph is moving upward and here it's moving downward, so that's why the imaginary part is increasing, so the damping frequency of oscillation also increasing. That's why the peak time will get decreased. What is the peak time? This is the peak time. If we plot the graph here, so this is the peak time. This will be a peak time. If the imaginary, if we move upward, or you can say that if you increase the gain value, so the imaginary value will increase, and if the imaginary value increase, then the damping frequency of oscillation also increase. So if the damping frequency of oscillation increase, then the peak time will get decreased. So the system will move toward the steady state in a very instant time. So now here if you see to the plot is in a straight line and it never crosses the imaginary part, so that's why we can say this system is always stable.